Welcome back for day 2. Hopefully you had a good rest after a very long first day. Learning using every day does not equal advanced user. That is a great note. So today we're going to talk about an introduction to Python for data analysis. This was originally kind of broadcast as Python for data analysis. But I think that I would be remiss to just jump right into that without at least giving some foundations of kind of what Python is, why we would want to use it for data analysis. And this is based very, very, very heavily on a talk that Tal Yarkoni gave at NeuroHackademy in 2019 that he pinned as Introduction to Python. So I've kind of pared his talk down, put that at the beginning, and then added some stuff towards the end. Hopefully we'll have enough time to get through it all, unlike the 1-hour introduction to Bash yesterday. So I'm going to do my best. As I said, I'm going to be going pretty quickly through this first part just so that we can get through all the content. My goal is to have a couple of breaks, one right around 10, one right around 11, before we then finish up at noon for lunch. So you can kind of plan your, getting up and moving around based on that. Plus or minus 15 minutes around those breaks. So before we get started, we are going to be working in Jupyter notebooks for most of this presentation. So for those of you who are aware of Jupyter, fantastic. For those of you who are unaware, very, very thrilled that I get to introduce these to you today. Jupyter notebooks are these fantastic documents that allow you to seamlessly integrate text via Markdown, code, images, figures, and etc., all into a single document. As I mentioned yesterday, the presentation I'm giving is actually written in a Jupyter notebook. So if you're familiar with how to load Jupyter notebooks, fantastic. If not, what I'm going to ask you to do right now is open a terminal. If you're using Windows, that's going to be the Ubuntu. If you're using Mac or Linux, that's just your normal terminal. Type Jupyter Notebook into the terminal and press enter. Again, if you're using Mac or Linux, that should automatically open a browser for you. If not, you may have to copy and paste the URL that's printed in the terminal into one of the browsers. Once you've done that, you should see a new little page, and you'll click New in the top right corner, and you'll select Python 3. And that will open a Jupyter notebook. Just going to wait a couple of seconds for everyone to do that. If you're having questions, confused about what's happening or how to open a Jupyter notebook from your terminal, please ping in the group chat. One of the TAs will be able to kind of quickly answer your questions. Can you repeat the instructions, please? Yep, so open a terminal, type Jupyter notebook into the terminal. If you're not automatically directed to a web page, that is, sometimes Jupyter will automatically open up a browser. Whatever is set to your default browser will be opened. If not, the terminal should print out a URL. It will say something like go to localhost / something 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 something. It's going to be a long string. Copy and paste that into your browser, be it Firefox, Chrome, Safari. Once you've done that, a new page will open up. You'll just click New in the top right corner and select Python 3, and that will open up a Jupyter notebook. You're talking about the Ubuntu terminal. Yes, open up your Ubuntu terminal. So if you've opened a Jupyter notebook, you will see a little cell. That little entry is called a cell, and you can enter code in that cell by typing into it, and then you can run that code by pressing Shift Enter. That will, if you press Shift Enter, that will, not working. I'm gonna have Jake or Loic, if you can maybe debug that. So you're able to enter multi-line code by typing it into the cell and then running code by pressing Shift Enter. To create a new cell, you can press the plus button on the left-hand side of the toolbar at the top of the screen. So I'm just going to exit out of this presentation for a second and show you. So I am in a Jupyter notebook. I've obviously populated it with quite a bit of information. This is the plus that I'm talking about up here. I can press that to add a new cell. So we're having some people who are having difficulties. Okay. So Alex is noting that if you get that error, try copying and pasting the link printed out into the terminal into your browser. and that will hopefully work. So the reason I'm going to ask you all to open a Jupyter Notebook right now is just to follow along with the code as we're going. You don't have to type all of the code that I'm going to be typing, but it is nice. It will serve as a reference. For those of you who are using Windows, as I said, the Windows and using the Ubuntu on Windows, it's likely not going to kind of open up the browser. So you will have to copy paste that link. All right, kind of going back into the presentation. So whenever I type code, you're going to type it in a cell. When I run it, I am pressing Shift Enter on my keyboard. You can press Shift Enter on your keyboard to run the same code. When you do that, a new cell, an empty one, should open up right below, and you can keep going with that. So to get started, it's just as a brief overview, what is Python? Python is a programming language, obviously. And so it's a widely used, very flexible, high-level, general-purpose, dynamic programming language. So we're going to dive into all of those because they all serve to make Python an incredibly useful resource for data analysis in Python, or data analysis in general. So widely used. Python is currently the fastest growing major programming language. You've maybe seen a version of this graph. This was posted on a Stack Overflow kind of summary blog. Python over the years has kind of overtaken some of the other major programming languages in terms of the most views of related questions. So it's right up there with JavaScript and Java. So yeah, sorry, I'm getting distracted by the chat. I'm gonna have to let Jake and Loic deal with that. High level. So Python features a very high level of abstraction. So for people who are more used to low level languages like C or C++, where you have to be very explicit about declaring everything in a ton of operations like memory allocation, garbage collection, Python just handles that for you. It lets you write code faster. You are just writing the code that is going to be executed without any of the scaffolding for it. So for example, if you are all familiar with Java, I took a Java class a very, very long time ago. So honestly, what I have written here is pretty much nonsensical to me. This is how file reading in Java works. You can see it's about 21 lines of code. I suppose we could cut it down if we got rid of some line breaks, but we can compare that to file reading in Python, which looks like this. So there is a lot less work that we had to do in order to get the same output. And it's general purpose. So you can do almost everything in Python. It has a really comprehensive standard library of tools and functions that it ships with. And then beyond that, it has this huge ecosystem of third-party packages. These are packages developed by outside people, Google, Microsoft, Apple, Amazon, Facebook. They all develop Python packages that they've provided back to people who are interested in using Python. And it's widely used in many areas of software development. It's not just data analysis, but you can use it for web frameworks, development operations, and as we will see, data science. One of the nicest features in my mind, this is not specific to Python, but is very nice, is that it's dynamic. So the code that you run is interpreted at runtime, which means that you don't have to manually compile it. When you run Python code, it is automatically compiled into bytecode and run. So the code that you read is the line-by-line code that's being executed. So that makes it so that you don't have to write your code, compile it, and then run it. It kind of eliminates a lot of those steps. The downside to that is that Python tends to have slightly poorer performance when you compare it to compiled languages like Java, C, etc. But there are ways to kind of try and eke out improved performance via some fancy tricks. I really like this XKCD comic. I like most XKCD comics. I think Elizabeth showed you an XKCD comic yesterday about Git. So this one is just, you're flying, how? Python, I learned it last night. Everything is so simple. Hello world, it's just print hello world. And so actually, if you try typing import anti-gravity into a new cell in your Jupyter notebook and running it, you will get a new web page, pops up right to this comic, which is kind of nice and fun. Nice little tie-in. So diving right into Python basics. So variables and data types. So we talked a little bit about variables yesterday in Bash. So in Python, we use the same syntax for declaring a variable. We assign it with the equal sign. I know for those of you who are familiar with R, you tend to use the caret hyphen, like the little arrow, pseudo arrow, or you can use the equal sign. Python uses the equal sign just like IEG MATLAB. Variables are pointers, not data stores. So this is important, and we'll get to this in a bit. But when you assign a variable, it's like putting a sticky note on whatever the value is. And you can have multiple sticky notes all pointing to the same value. So we'll come back to that at a later point, but it is worth noting, if you're familiar with programming, that these variables that we assign are pointers. Python has a number of different data types and structures, all of the basic ones that you would think that you need in a programming language, things like Booleans, true, false, numbers like ints, floats, complex, etc., strings, lists, dictionaries, and a bunch of others. And the nice thing is that we don't have to assign a variables type assignment. So we can just say, you know, this equals this, and we don't have to specify what data type it is. Python will just infer that based on our assignment. So perhaps one of the easiest things to demonstrate in Python is just that you can use it as a basic calculator. So for example, addition, 1 + 1 works and we get 2. Multiplication, 2 × 3 works and we get 6. Division, 10 divided by 3 works and we get 3.3333333. I'm going to pause to make a note here. Python 2, which is now kind of end of life, you should not be using Python 2 anymore. It kind of quote unquote died earlier this year, finally. In Python 2, when I did 10 divided by 3, it would give me something very different. It would actually give me, oh, Jesus Christ. Sorry. 10 divided by 3 would give me what is now known as floor division, which is 10 divided by 3, doubled forward / 3. So floor division says divide this and then just get rid of any remainder. So how many times can 3 go into 10 without any excess? This is what Python 2 used to give you with this syntax. Now Python 3 gives you exactly what you expect. We expect 10 divided by 3 to be 3 1/3. Exponentiation, raising things to the power, that works like this. 3 to the 3rd is 27. And then modulo. So modulo, for modulo, we use the % 2. That will give me 0. So modulo basically says, what is the remainder of this operation? If I divide 4 into 2, how much is left over? We can demonstrate that a bit more easily with an imperfect modulo. So 5 modulo 2 is 1. That is, 2 can go into 5 twice, and then there's a remainder of 1 left over. So this is the basic math built into Python. There's a few other minor things, but these are the syntax of all of the things that you'd expect. So for variable declaration, we generally want to store the outputs of our commands that we're running. And the way that we do that, as I said, is with assignments. So if I do output equals 3 + 5 × 4, that is now stored in the variable output. I can display that by typing print output, and I get 23. Note here that Python does obey the order of operations. So from your second, third, fourth grade PEMDAS, it will do that rather than just reading from left to right. The nice thing about storing variables is that we can use them in new operations. So I can do print output × 10, and I will get 230. So obviously this is critical to maintaining, data as you go along in a data analysis pipeline, that we're storing things in variables. Importantly, variable names can include letters, digits, and underscores. They cannot start with a digit. So I could not say, 10 output equals 3 + 5 × 4. That does not work. And they are case sensitive. So weight 0 is a valid variable name, whereas 0 weight is not. And then weight with a lowercase w versus weight with an uppercase W are different variables. Going through some basic data types. So an integer here we can say, so age in years, let's say we're 20, that'd be nice. Note the naming convention that I've used here. So in Python, you're recommended to, one, be very verbose in your variable names. So actually Python tends to get not unhappy, but it's considered bad practice to use things like I or L or things like that when you're going along. So verbosity is encouraged in your variable names. And then moreover, Python uses underscore delimited names. So when you would normally have, a space or something, it's encouraged to do underscores versus, if you're more familiar with, JavaScript or something, this would be camel case where you've capitalized the kind of different words. Python prefers this. And so we will be using that throughout the rest of the course, and I encourage you to do that in your own code as well. We can store, as I said, floats, so almost pi, 3.14, that works. We can use a string, banana, B is for banana, if I can spell. That works. We can assign strings to variables. Note here that I'm using single quotes. I can just as easily use double quotes. However, you cannot mix quotes. You need to have the same type of quotation at the start as at the end. We can do Booleans. So for example, enjoying this tutorial equals true, being bored equals false. Those are both valid Booleans in Python. And then Python has this special thing called a none type. So it means that there's no value. It's not 0, it's not false. It just means that like nothing exists. And when you run a function that doesn't explicitly return a value, we'll talk about how you return values from functions in a second, it defaults to returning none. None is just kind of a placeholder, it's empty, and it doesn't work in any operations. I can't multiply none by 2, or I can't add 10 to none. None is just nothing. I am going to take a quick break for a second just to address some of the questions and stuff that's been happening in the chat. It looks like Jake and Loic have been helping everyone get set up. Appreciate that. Were we supposed to download the course material? The course material is on OSF. No, you do not need to download it for the purposes of this presentation. You can just work in an empty Jupyter notebook and type the code that I'm typing as I type it. That is perfectly fine. This lecture will be recorded, or is being recorded actively, and we will upload it with the utmost haste, although post-processing of these videos and uploading to YouTube does take a bit of time, given that everyone's internet bandwidth under coronavirus has been downgraded substantially, since everyone's using the internet all the time now. So we'll try and get this online as quickly as possible. The Python notebook that I am working for is available in 2 formats on the course materials. One is called Python for Data Analysis -empty, and that is what I am working on right now. There's another just called Python for Data Analysis.ipynb, which is an IPython notebook what we're working in, and that has all of the code that I am typing as I go along. So you can refer to the kind of non-empty notebook for future reference. That's going to have everything, so you're not going to like lose out on all of the code that I'm typing or any of these notes or resources. All right, so most code requires us to do things beyond just assign numbers, basic floats, numbers, strings to variables and work with those. We need kind of more complex data structures built out of the basic data types. And so Python has a lot of built-in support for some of the most common structures that you would use. And then some additional structures can be found in this built-in library called the collections module. But beyond that, actually, a number of external resources there are some external resources that provide even additional data structures that we'll get into later in the program. So the first thing is a list. So we can make a list, let's call it random stuff. And the way that we construct lists is with square brackets. And so we can add anything to this list. We can add integers, we can add floats, we can add strings, banana, and that all just automatically stores it right in the list. And then we can see what's in this list by indexing it, it's called. So if I want to index a list, what I do is I type the name of the variable and then square brackets without the equal sign, just right next to it. and I type the index that I want to extract. So in Python, indexes start at 0. This is very different from MATLAB, where indexing starts at 1. And so this does take some getting used to. So if I want the first item in my list, it is the 0th index. I can also take slices. That is, if I want a few items in the list, rather than doing this and individually typing them out, I can say, I want everything in my list up until the second item. So this will give me the 0th and the first, but not the second. Slicing in Python is exclusive, so it goes up to, but not including the number that you've specified. Negative integers, if we use them as slices, start from the back of the list. So here I went from the beginning up until the second, but up until but not including the second item in the list, or the index 2. Here I say from the -2th index, I want everything until the end of the list. So banana here is the -1 index, 0.1 is the -2 index. So this should return to me 0.1 banana, as it does. And then we can oh, wow, interesting. Just give me a second to pop out of here. So we can append elements to lists by using a method. So objects in Python have these things called methods. The way that we access methods on objects is by typing the name of the variable and then dot, and then the name of the method. In Jupyter, as within Bash, there is tab completion. So if I type random stuff dot and then I type tab, it's going to give me some of the options of the methods of this object. So lists have by default these 10 or so methods. If we want to append an element to a list, we use the method append. So I can type this, append 4. And then I can see what my list looks like that. I can also modify elements in lists. So if I do random stuff 0 equals, let's change that to 10. The way that I modify is I say, all right, I want the 0th entry of random stuff, and I'm going to assign it to 10. So now when I look at my list, I have 10, 0.1, banana, 4.0. So the nice thing about lists is that they are what we call mutable. You can change them, as we've done here, this modifying and appending. And they can store all the different data types available in Python. So you can have ints, floats, strings. I can have lists inside lists if I wanted, and so on and so forth. Tuples are very similar to lists in that they can also hold all the different data types, ints, floats, strings, etc., but they are immutable. That is, they can't be modified once they're created. So tuples are initialized with parentheses, not square brackets. So for example, I would say my tuple equals parentheses 10, 11. Now I can subset tuples just like lists. My tuple, I want the 0th entry, that should be 10. But I cannot change tuples. So this worked on a list, but it does not work on tuples, and it yells at you for just that reason. This is nice because sometimes we accidentally are, you can accidentally try and modify something that you shouldn't be modifying. And so using tuples is very valuable in those instances when you really shouldn't be changing data. Next up, we have dictionaries. So dictionaries are actually no longer unordered, but we'll keep that for now. You can think of them as unordered collections of key value pairs. So you can access dictionary elements by key, but unlike lists, you can't do positions. So I can't say I want the 0th item in a dictionary. So the way that we would define a dictionary is let's define some fruit prices. So for example, an apple, let's say that costs 65 cents. A mango, let's say that's a bit more expensive, that costs $1.50. Strawberry. Here in Canada, I've found that strawberries are actually incredibly expensive. So let's say that those cost $5 for a pint. I am from the States originally, so we use stupid measurement systems like pints. And you are going to not be able to get a durian in Canada. So we'll say that that is an unavailable fruit price. So notice that we're using these curly brackets to create our dictionary. And the way that we define it is we have our key, which needs to be a string. And then we use a colon and then the value associated with that key. And then we can separate key value pairs in this with commas, just as we would with the lists or tuples. So now that I've created that dictionary, we can easily query the values via the keys. So the way that I would have done a list is I would have said fruit price is 0, for the 0th entry, but instead I can say fruit price is apple. And what it will do is it will return the value associated with that. Yes, keys can also be integers. Thank you, Jake. That is a good point. So I could also say 10, 10. But I can't say, we had our list before. I can't do that. Lists do not work as keys in dictionaries. We can add new entries via assignment. So the same way that in lists, we were able to, yes, the tuple can be a key as well. Thank you, JB. So the same way that we, in a list, we're able to, override variables. We can add new variables here. Let's say I want to add the cost of a pear. I can do that just by saying fruit prices pear equals $1. And now fruit prices will have my added entry of pear. In the same way, I can change values of keys that already exist. So I can say apple. Now I want that to equal $1 as well. And my apple is going to be updated to 1. So in dictionaries, assignments and adding of new entries is done via the same syntax. So the interesting thing about Python that's perhaps not immediately intuitive is that everything is an object in Python. You may have heard that Python is called an object-oriented programming language, and that's because everything that you see in Python is a data object. So all of these data types, the ints, the floats, etc., all of them are just objects. Everything is an object. The operations and the things that you do with a variable depend on the object that it's pointing to. So for example, the multiplication operator that we use, the asterisk, we can do that for some objects, but not others. So we can multiply, an integer by 2. That's fine. We can multiply a float by 2. Also fine. We can actually multiply a string by 2. What it will do is it will just return that string duplicated, or however many times we've multiplied it. What about a list? We can do that as well. It will just repeat the values in the list and create one big list. What about, for example, a dictionary? So if I say pear is $1 times 2, I get an error. Unsupported operand types for star, dict, and int. What this means is that I cannot use the operator star multiplication for a dictionary in an integer. That's not defined. It doesn't know what it would do. Critically, dictionaries can't have two entries with the same key. So I can't say pair 1 and then pair 0.1. That doesn't work. And so, this idea of multiplication, where I would effectively try and do this doesn't make sense for the purposes of a dictionary. And so it's not there. Python raises this helpful type error message. There's different types of errors that you get in Python. There are quite a few that are defined. So when you see this, it means that you're doing something that isn't defined for that object. Python, of course, has control structures, just like you might be used to in basically every other programming language. And these are features that allow you to control how the code is executed. So for example, you can do iteration with for loops or while loops. We can do conditionals with if then else statements. So let's try and do an if then else statement. So we're going to define two variables, a equals 1 and b equals 0. And then we're going to try and determine which of these variables is greater than the other. And the way that that works in Python is I can say if A is greater than B, print A is greater than B. If I wanted to, I could end it at this. The nice thing about if, else statements in Python is you only need to, if the if portion is the only required portion. So I could do this. Yes, A is greater than B. That's exactly what we would expect. Alternatively, I can add an else clause. I can say print A is not greater than B. Obviously, A is greater than B, so we don't trigger this. But what happens if A and B are the same? I now have A is not greater than B, but that's not true, they're equal. And so what I can do is I can say, add an elif clause, elif A equals B, print A is equal to B. And now I get A is equal to B. And so the way that if, elif, else statements work in Python is that it goes through each of them. It checks this, does this evaluate? It's true, is A greater than B? If so, I'm gonna execute this command. If not, I'm gonna run to this line, is A equals to B? And this is how we test equality of integers or floats or numbers or strings and such in Python, this double equals sign. Note that it's different than the single equals, which is what we use to assign a value to a variable. If A equals B, I'm gonna print this. Otherwise, I'm going to print this. Importantly, Python cares a lot about white space. So you'll notice here that there's this indentation between the if line and the print line. That is 4 spaces, 1, 2, 3, 4. Python indentation works on the 4 space rule. So if you ever have indentations, it has to be 4 spaces. This will not work. Interesting, Jupyter is just gonna prove me wrong. Great, Jupyter. This should not work in any normal Python interpreter. You can see that this print command is turned red and then is turned green when I indent to an appropriate line. Jupyter is doing something that I actually fundamentally disagree with here, and it's kind of hiding some design flaws from us, but that shouldn't work in Python. We'll talk about why Jupyter is nice in the future, but sometimes it chooses to do things to make your life easier that in the end actually may make it a little bit more difficult. Jupyter is too smart, it absolutely is. So other control features, we're gonna go for for loops now. So if we want to loop over the random stuff list we created earlier, as a reminder, this is what our random stuff list looks like. The way that we can do that is we can say for element in random stuff, print element. And what this is gonna do is on every line, it's going to print in consecutive order, 10, 0.1, banana, and 4. And so this is the syntax for doing that. So anything that you can iterate over, so this is called iteration, like lists or tuples, this is the syntax that we would use for that. We could also, instead do things to this. So we said that all of, the strings, floats, and ints all support multiplication. So we can instead print element times 2. That works as well. A shorter version of that, if we want to store the outputs of our loop, is something called a list comprehension. So let's say that I do want to duplicate every element in my random stuff list. I want double stuff. The way that I write that is I would write it as though I'm constructing a new list. And then I would write element times 2 for element in random stuff. And let's print double stuff. And so we can see what I've done is I've constructed a new list that is equivalent to random stuff, but each element is duplicated from its original value. And you can see the similarity between this and my for loop up here. It's kind of flattened. And so these are a little bit more difficult to read at times. They can get quite long and complex with other conditionals and so on. But it is really nice if you need to iterate over something and you want to store the outputs of that iteration to use list comprehensions. And then finally, we can try a while loop. So let's define a new variable, I equals, let's say 0. While I is less than 5, I want to print I. And then, so that I actually increment, I want to add 1 to my I variable. As I said, using single letter variables is not a good good things. So so instead of I could have called this, counter. While counter is less than 5, print counter, and then counter equals counter plus 1. And so what this will do is then it's going to go and print 0, add 1 to itself, come back up here. Is counter less than 5 still? Yes, it's only 1. Prints that, add 1, and so on and so forth. So you can see that we get 0, 1, 2, 3, 4, just as we would expect, because we set the upper limit as 5. And so that is all for control structures. So we just went really quickly through some of those. Again, we're going to keep going quickly through this. I think we'll get through the end of this kind of very, very fast intro to Python data type structures and things by about 10 o'clock. So I'm going to pause for questions then, but if you have anything urgent, feel free to type in the chat. One of my favorite things about Python is namespaces and imports. So I am self-taught in programming. My first programming language that I worked in was MATLAB. I used that for a little bit, and then I went to R, used that for a little bit, and then I went to Python and kind of landed there, and that's what I've been using since. Back when I originally started using MATLAB, MATLAB doesn't have this idea about namespaces and imports. R does. They're like libraries. So when you say like library, whatever, ggplot2, that's importing the ggplot2 library into your namespace. But Python is very, very serious about maintaining orderly namespaces. So there are some built-in commands that you can use. But if you want code outside of what is built into the base Python programming language, which isn't a whole lot, you need to explicitly import that. And so this import system often annoys people because they're like, well, wait, why can't I just call this? I need this value and Python has it, but why do I have to explicitly define it? And the reason you have to explicitly define it is because doing so increases the clarity of your code. When you have to specifically say import something, some code that I need, when someone else comes along, they know where that's coming from. And so this eliminates naming conflicts and confusion. I am not a huge, it's been a long time since I've used R, but I definitely remember when you're using R and you load multiple libraries, a lot of times you'll get a bunch of error warnings. This conflicts with this is now, masking this other function. And Python has systems to kind of totally eliminate that. So there are 3 different ways, at least, to import and access things from packages in Python. So there's this built-in Python library called the math library. If you want to do things with math, this is a very useful library. So the way that we would import this library is by typing import math. And then let's say we want the pi value, math.pi. So once we've imported the library, we can access its values using the same dot notation that I mentioned before. So if I print math.pi, that gives me pi up to a certain precision. Another way to do the imports is from math import pi. So here, rather than importing the entire math library, I'm just importing what I need, which is pi. And now I can just say print pi, and I get the same exact thing. Finally, if I wanted to, I could use this from math import pi as pi. Let's say I'm an old school mathematician and I like all of my constant variables to be defined in capital. And so as we noted before, Python is capital case sensitive. And so I want to do that. And so from math import pi as uppercase pi, and I print pi, that prints as well. So these are kind of 3 of the most common ways that you'll see things imported into the Python namespace. We're going to be using these notations quite frequently throughout the rest of the course. And so there are tons of different libraries in Python, and it can be a bit confusing to figure out which one you need to import. Again, here, just blatant Googling is your friend. How do I get pi in Python? Will return probably the primary Python documentation website, which is really fantastic, very verbose, very clear, easy to read. And that will tell you, oh, pi is in the math library. So you need to import math in order to use it. JB notes that it's good practice to keep a namespace for what you import. Don't import everything in the same namespace. So what he's recommending is to use something more like this first notation where I import math. And then when I want to use pi, I explicitly say math.pi. That way it's very clear that my pi variable is coming from the math library. If I do from math import pi, later on, I could accidentally say pi equals 3.14. And then I have now overwritten this. And so I can I can no longer access that because I've assigned a variable over it. And so it's good to kind of keep things like this. And so that avoids you accidentally redefining your variables and overwriting them. And it just makes it a little bit more clear for everyone who's reading your code. So next up, we have functions. So functions are a block of code that only runs when you explicitly call it. It can accept parameters that alter its behavior, and it can accept any number of types of inputs. But if a whole library is imported, does it take more RAM space compared to importing just a variable from the library? That is a great question, and I'm actually not totally sure on the answer. I don't believe so. So generally, importing libraries in Python, you shouldn't be too worried about RAM space. They're going to be far less space than the data structures that you're defining. So for example, import math isn't going to be a huge cost if I then have a list of 20,000 values. But yes, as Jake says, importing a large package can take some time. Importing just one function might be instantaneous. This very, very much depends on how the package is structured. So you're going to have to play around with that a little bit. But the most commonly used packages, especially the ones in the standard library that are kind of built in, shipped with Python, those are very, very, very quick to load. Third-party packages developed by other developers, not explicitly by Python, are the ones that can take kind of a variable amount of time to load. So coming back here to functions, we talked about functions yesterday in the Bash tutorial, like ls, pwd, etc. Those are functions in Bash. In Python, Python has some built-in functions, but we can also define our own functions. And that is probably the most common thing that you'll be doing when you want to write workflows. If you find yourself typing the same 3 lines of code over and over again to take a value, multiply it by 2, and then add 3, maybe you want to consider using a function. So I have the outline of a function here that we're going to fill in, but I'm going to go through this. So random is a built-in Python library, and it allows you to generate pseudo-random values. So if I want to generate 100 random, numbers between 0 and 1, this is the package the library that I'm going to go to do that. So this first line here, def add underscore noise, parentheses x, comma mu, comma sd, parentheses colon, is a function definition. So when we are defining a function, we use def as in define the function, and then the name of the function, add underscore noise. And then we do parentheses, and inside the parentheses are the parameters or inputs that the function is going to take. So here our function add noise is going to accept 3 parameters, and we're going to call them x, mu, and sd. And then we're going to do a colon to say everything after this is now the actual function itself. Functions in Python generally come with these little what are called doc strings or documentation strings. And so when you're writing your own functions, I strongly encourage you to write these in a format very similar to this. Usually what happens is the first line gives you an idea of what the function is going to do. So our add noise function is going to add Gaussian noise to an input. Our parameters that we're accepting are x, a number, that's what we're going to add the noise to, mu, which we'll accept should be a float, and that's the mean of the Gaussian noise distribution, and then SD, which is also a float, and that's the standard deviation or the breadth of the noise distribution that we're going to generate. And then the function is going to return a float. So you'll notice here that there's these 3 double quotes that encase this, this documentation string. And so that is how you write a docstring. So you use 3 double quotes, type your documentation with line breaks, and then you end it with three more double quotations, and then you can start typing code. So everything after this line 20, everything here is now going to be the code that the function runs when I call it. And so what we're going to do is we're going to say noisy equals random.normal variate mu sd. So random here is this package we imported. Normal variate is a function within the random package, and it accepts 2 parameters at least, mu and sd. Mu here being the mean of the distribution, sd being the standard deviation of the distribution, and we're going to add that to our x variable. And then we are going to return noisy. So we have to explicitly tell our function what values we want to return from the function. Yes, so Melissa is raising a point in the chat that is really important. When I type 3 double quotes, I get this when I type the third, which is you get 3 additional double quotes. Basically, Jupyter is being smart again and saying, oh, I think you're typing a docstring. You just typed 3 double quotes. I assume you're going to want to end that docstring at some point. So here's the 3 double quotes that will go on the end. You just hit enter a few times, and then you can type your docstring here. So what we've done here is I'm calling the parameters of my function right here. So I have x, this is going to be the x that's provided here, mu, that's the mu that's provided, sd is the sd that's provided. I can define new variables inside my function, but then if I want to be able to access them outside my function, I have to explicitly return them. So to demonstrate this, what I'm going to do is I'm going to exclude that return line. I'm going to execute this. Notice that nothing got ran, or nothing was printed to the screen. So now I want to add noise to my number 10 with a noise distribution of a mean of 0 and a standard deviation of 1. And I hit enter. Nothing was returned. So why not? Let's say I want x. What is x? Print x. X is none. So this is now coming back from the beginning when I mentioned that none type in Python. If I don't explicitly tell my function I need to return this variable so that anyone who calls this can assign it to something, I get none. So what I need to do is I need to use the return noisy. And so now what I'm saying is every time someone calls this function add noise, make this new variable noisy, and then provide that back to the user. So if I do that, re-execute this cell, and now I'm going to rerun this line. So x equals add noise 1001, print x. I get x is now 8.280, blah, 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 blah. You're going to get something different, again, because we're using this random library. It's going to be, provide you random numbers every time you run it. So actually, if I just keep running this every time, I'm going to get a slightly different number. There are ways around that we can maybe talk about later on in the week for ways to make your code reproducible when you're using these sorts of random variables. But for now, suffice it to say that is how that's going to work. So Python has this really nice concept of positional versus keyword arguments. MATLAB and R do as well, as does, I think, basically every programming language. But the way that they work in Python is that positional arguments are defined by position, and they need to be passed. So if you don't provide a positional argument to a function and it expects it, it will say missing an argument. You need to provide, for example, x. And then the arguments in the function signature are filled in order. Keyword arguments, on the other hand, have a default value. You don't need to provide them, but you can if you wanted. So returning to our function that we defined above, now we're going to add noise with defaults. So again, same outline, def to define our function. The function name is add noise with defaults. X here is our positional parameter. And then mu and sd are now keyword arguments. And you can tell they're keyword arguments because they have default values. And the way that we write that is mu equals 0, sd equals 1. So by default, if someone calls this function, mu and SD are going to take the values of 0 and 1 unless someone explicitly says otherwise. So you can see that I have more or less the same documentation string as above, but now for my mu and SD, I've added to the documentation string that the default is 0 and the default is 1, and that those parameters are optional. This is really helpful for people who are using functions that you might write, or even for yourself. I think Elizabeth said it best yesterday with Git, that you are your, you're your own collaborator 6 months in the future. And you don't answer emails. So writing doc strings on the code that you're creating is very, very important. And so the way that this works is, again, we're just going to redefine the same thing, normal variate, mu SD plus X, return noisy. And now when I want to call it again, add noise with defaults, I can just do this. I can just provide X, which is 10, and I'll get a random number. I don't need to provide mu or SD, but I can. So let's say I don't want to provide mu. I want that average, the mean of the noise distribution to be 0. I can provide SD. Now I want SD to be 10. So my noise distribution has a much wider width. And again, the number that I'm getting is now far different from 10. I can also optionally provide mu if I wanted. So now I want the mean of my distribution to be 10 as well. And so that's going to provide me even different things. Note that for keyword arguments, I can provide them out of order. So in our function definition, we had mu equals 0, SD equals 1. I can say SD equals 10, mu equals 10. And that is important to know. I also don't necessarily have to specify that these are keyword arguments when I'm calling. So I could say 10, 10, 10. Well, for the purposes of demonstration, it might be easier if I provide these all differently. 10, 0, and 1. Here, these are read in order from left to right. So 10 is assigned to X, 0 is assigned to mu, and 1 is assigned to SD. I cannot do this. I cannot put a keyword argument and then a non-keyword argument after it. So if I'm doing keyword arguments, everything thereafter has to be defined as a keyword argument. So with that, I think we've come to the end of our kind of very brief intro to Python syntax, data types, data structures, etc. That was a lot for those of you who maybe had answered on the poll that you'd never once or only a few times used Python. For those of you who are in the higher brackets, hopefully a lot of this was kind of refresher. But yeah, I think now we'll take some questions on anything that we've covered so far, and then we'll take a 10-minute break before coming back. So let's look at some questions. If you were to call the add noise with defaults another time, does it take the original mu SD values or the changed ones from the previous command? That's a great question. So you're saying, let me make sure that I understand what you're saying. So if you're saying I do this, where I assign mu and SD to 10, and then I do this with defaults 10, is my mu and SD 10, or are they 0 and 1? They are 0 and 1. So this mu and SD only correspond to the time that I'm calling the function where I define them. If I don't define them, they take these default values. These values are not overriding the values that I have set as defaults for in perpetuity. They're just that one time. So we can show this. It's a little bit difficult when you're using random numbers to show how this works. So let's do x1 equals x2 equals. So if I print x1 and x2, because they're random, this is obviously going to be very different. But with a mu and SD of 10, I get a number that's far more different from 10 than when I have my default settings. Does anyone have any other questions about anything we've gone over thus far? How would importing a package as import math.py differ from the other options you stated? So if I type import math.py, I get this error. So no module named math.py. Math is not a package. I can't do that. So because, so when it says math is not a package, this isn't the most helpful error message. It's actually a little bit misleading in my mind. Really, the issue is that pi isn't a package. So sometimes, and we'll get into this a little bit late, actually we won't get into this later, but sometimes packages can have multiple kind of nested sub packages. And when I can import them like that, but because pi here is a variable, I can't just import that directly. So I would need to say import math or from math import pi. That's the only way that works with that. Someone asked, can I please re-explain what is the use of the return function? Yes, so return is saying, okay, when I've written this function, I've taken my inputs, I've used them to calculate some new variable, and now I want that variable to be accessible outside the function. So let's, instead of return, let's print noisy. Add noise with defaults, 10. I've printed 9.51, so I know that that is the value that noisy takes. But now, if I do this, I want to say, new noisy value equals add noise with defaults 10. I want 9.51 to be assigned to my new noisy value variable, and then I do print new noisy value. Noisy is now 10.022, but my new noisy value does not take on that value. It says it's none. Effectively, this is more to do with Python's kind of idea of namespaces. Functions have their own kind of defined, self-contained namespace. If I want the variables in my function's namespace to be accessible outside my function, I need to specify that I am returning them. And returning says, make this available outside the function. So when I use return, that says that whatever noisy is in the function, I can assign that to a new variable outside the function. So now I've done this, it's printed noisy, 10.4, and now my new noisy value takes on that same variable. Can you return more than one value? Ella asks. Yes, absolutely, I can. So I could, if I wanted, return noisy and noisy times 2. And the way that I would do that is I would just separate them with a comma. So new noisy value and then duplicated. And so the way that you would then make sure that you get those is by, when I'm doing the equal sign, I can have both variables outside. So what will happen is I'm going to get noisy and noisy times 2. Noisy is going to be assigned to new noisy value, and noisy times 2 is going to be assigned to duplicated. And then I can print those both here. Cannot unpack. Ugh. All right, well, apparently we have to enclose them in parentheses, which doesn't quite make sense to me. I don't think that's right. But anyway, so you enclose them in parentheses and then you separate them, and you can do that. Yes, nothing is executed after return line, so can be used to exit a function. Yes, Edouard points out that if I did something like this, print noisy times 2. So I have, let's just get rid of noisy times 2. I just want to return noisy. We're going to get rid of this print line. So if I did that, here, what's going to happen is I'm going to enter my function, make a new noisy value, return that value. This line is never going to get executed. So I will never print this. Anything but low or return value. Return basically says function stop, provide this value back out to the main namespace and finish. So here, there we go. I forgot to re-enter. So now I don't see my noisy value printed. It's just assigned to a new noisy value. Danielle, oh, sorry, Ashraf. Is there the equivalent of a break and error management throw, catch, try? Yes, there is a version of breaks and tries and accepts. Absolutely. So that it's very similar to what you expect. So try and accept is basically a way to say, I want to try doing this. But if for some reason it doesn't work, it throws an error, I want to do this other thing instead. The way that we might handle that, let's give it a go. I'm just going to clear this cell just for the sake of demonstrating. We said that we can't multiply dictionaries, right? So try to multiply a dictionary pair times 2. But if that doesn't work, print cannot multiply dictionaries. And so what happened here is, rather than hitting this error, which as a reminder looks like this, I instead chose to do this. And so that works. And then the equivalent of a break. So break is when, say, you're going through a loop, you're iterating over a list or something, and you want to stop at a given point. Break will just say, you know, stop here, exit out of this loop, and keep going. That's perhaps most clear in while loops. So if we're doing, you know, our counter equals 0, while counter is less than 10, print counter equals counter plus 1 plus 1. And then if counter equals 5, break. So now what's going to happen is I set my counter to 0, I enter this while loop, so I should go through this while I'm less than 10, and I'm going to print the value of counter and then add 1 to it. If I reach this line and counter is equal to 5, I'm going to break out of this loop. That is, the loop will not continue after counter equals 5. So what I'm going to do to show that is print counter afterwards. So counter went up to 5, and then it exited the loop. It looks like Loic answered JB answered Danielle's question. JB is pointing out his discussion about importing things into the same namespace, and just that you really should be using the libraries. You should be using that import math and then math.py. So we just went through very quickly in an hour Python syntax specifics of the programming language. And so now I'm going to try and motivate a little bit about why I think you should be doing data science in Python. Yeah, we'll just get into it. So Python is, despite what some people say, it is relatively easy to learn. Obviously, this is relative, but it has a readable, very explicit syntax. Its strength is that it uses white space and indentation to create kind of concrete sections of the code. And so that makes it a lot easier to look at rather than just no white space, you know, a big wall of code text that you need to be searching through. Most packages are very well documented. For example, for those of you familiar with scikit-learn, Stephanie Suarez and Jake Vogel are going to go over that in a talk on Thursday. The documentation of scikit-learn is widely held up as like a model standard. And it is fantastic. Their documentation is equal parts Python tutorials and equal parts machine learning tutorials. And because Python is so popular now, there's just this huge number of tutorials, guides, and other educational materials that are accessible on the web. It's very easy to find things that will help you, quote unquote, like learn Python. As we mentioned, it has a really comprehensive built-in library of code. So this is called the Python standard library. These are things that ship with Python. As I said, they're developed by, you know, the Python core developers. They're not developed as much by third-party people. When in doubt, it's a good idea to check whether or not Python has a built-in tool for you before you write your own. For here, a list of some of the kind of very common, very helpful standard package libraries are the OS library. You'd get that via import OS. And this has operating system tools. So everything that we talked about being able to do yesterday in the bash shell, you can do using the OS library. There is the tool, import RE, and this is for regular expressions. Regular expressions are a headache for everyone. If you've never heard of them, that's fine. If you have, you know that they are a headache for everyone, but they are still incredibly useful and powerful, and so Python has a package dedicated to working with them. Collections, I hinted at earlier, has some useful additional data structures, things like dex, default dictionaries, and other such things that you might find useful if you need to create kind of complex code that relies on those data structures. Multiprocessing, this is a really nice tool for parallelizing your code if you're doing a lot of things that a lot of very simple tasks that can easily aren't interdependent. Multiprocessing is a way to make those happen faster. Pickle is a method for serialization. So if you need to be saving things and loading them to and from disk very rapidly within Python for your own code, Pickle is a nice way to do that. And then JSON, if you're familiar with JSON at all, there's a package for reading and writing with JSON, which makes interacting with web applications incredibly fluid. But Python really shines in its external libraries. So I think that, R is perhaps one of the best mirrors to this. The external libraries for R are unbelievable. MATLAB has a few external libraries that are good, but it has significantly fewer. It's a lot more relies on MATLAB's built-in toolboxes. Python's external libraries are kind of exceptional. And it has really good packages for just about everything that you could think of. For data science in particular, there's kind of a core set that everyone uses. But there's things for web development, for databasing, for scraping, for natural language processing, machine learning, image processing, plotting, GUI development, testing, et cetera, et cetera, et cetera. The list just kind of goes on for days. This line here, so I did mention that this slideshow is built off of Tal Marconi's Introduction to Python lecture at Neurohack Academy. He has this line, package management is easy with Conda and pip. This is true to an extent. Conda and pip do make installing these external libraries in Python a bit easier. But for those of you who have dealt with Python installation issues, it can be very frustrating to work with. In RStudio, install.packages usually works, although I have run some very interesting errors with that. With MATLAB, all you need to do is you download a folder, you add it to your path, and boom, you're done. So Python, I think, is getting better. Conda is relatively new, and it's making things a lot easier to install. You all hypothetically should have used Conda to install the Python environments that you're going to be using for this course, and hopefully that was pretty seamless for all of you. But if you have issues or errors in the future with installing things, Conda and pip have pretty extensive documentation online. Stack Overflow is obviously a great place to go for those sorts of issues as well. Python has relatively good performance compared to other languages that you might kind of compare it with. It's a high-level dynamic language. As we said, we don't need to declare the types of our variables when we assign them. So I was able to say, age in years equals 20 without needing to specify that age in years is going to be an int. I was able to specify that, random stuff was a list by just saying random stuff equals and then a list without pre-specifying that it was a list. But that comes at a performance cost. It's not a huge performance cost, but it is a notable performance cost. I would argue that for most of us in research, the performance cost of Python being a dynamic language is not super relevant. It's relevant for companies who are designing things that need to be really quick and snappy. But for our purposes, the difference between waiting 1 second for something versus 2 seconds for something isn't going to be a huge hurt. And in general, the less Python code that you're writing, the better your performance will be. So what that means is that the standard library code packages and things like NumPy, scikit-learn, pandas rely really heavily on C, C++, or even Fortran functions. I don't ever want to code in C, C++, or Fortran myself. I have no intention of doing that. But by calling that Python code, I get the performance boost of having written code in C, C++, or Fortran. And so the rule of thumb, the general rule is that you shouldn't be writing things yourself, like when you need to, compute a correlation. You should be relying on code from, for example, NumPy. NumPy has much, much faster ways to do correlations than you actually writing out the code yourself. I think it's worth kind of here just showing how Python compares to other data science languages. Some of you from your surveys you filled out have a significant amount of experience in other languages like R or MATLAB, which is fantastic. I am not a purist. I am very happy for people to use whatever language is best suited for them. And best suited for your environment. I would argue that neuroscience is a bit split at the moment. There's a significant amount of neuroscientists that use MATLAB, and then there's a significant amount that use Python. There's a smaller community of neuroscientists that use R, but I find that R is a lot more common in like pure psychology. Pierre makes a quick note in the chat about packages that they require compilation in MATLAB and they can be harder to install. That's great. I will throw that in when I'm making the comparison to MATLAB in a sec. So R is dominant in statistics, of course, and as I said, I think that psychology has kind of picked up R as its main programming language as well, and it attracted a lot of people who maybe were coming from more point-and-click interfaces like SAS, SPSS, and Stata. It has exceptional statistics support. I would argue that statistics support in R is better than in Python. And I actually think that there are a lot of people who would agree with that. That said, that doesn't mean that you can't get the best of R in Python, and we'll talk about that in a little bit. R is designed to make data analysis and visualization as easy as possible. So yes, Kat points out it's possible to have R in Python. We're gonna get to that. R is very kind of quick and easy to do things in terms of getting that, but the actual code itself is quite slow. Also, because it evolved from a precursor language, language quirks can drive a lot of people who have software development experience and are coming into R really, really crazy. I'm not going to get into them, but there are a lot of really kind of frustrating things in R from a software development standpoint. And then there's less support for things not related to data. There is growing support. I would say that the R community is kind of exploding right now, but for things like web development, databasing, management, and stuff like that, R doesn't have the same chops as Python. MATLAB is a proprietary numerical computing language widely used by engineers because of how many engineers there are in neuroscience. I would say that neuroscience has quite a lot of MATLAB people. Good performance, very active development. There's releases every biannually, so that is twice a year, I believe. They have new releases and then with bug fixes and stuff in the interim, but it is expensive. For those of you at, for example, McGill, McGill has a site license, so you pay nothing to use MATLAB. For those of you at other universities, your university may not have a site license. So at my old university, if we wanted to use MATLAB, every MATLAB license we purchased was $500 a year. That doesn't seem like a whole lot in terms of a research budget, considering that putting someone through an MRI scanner costs maybe in the realm of $500 for a single session of 2 hours, but that is quite an expense. And because it's a closed ecosystem, because it's not open source, it's not developed openly, there aren't as many third-party libraries. There is an open source port, Octave. It looks like Pierre is in the chat now, and he, I'm sure, can tell you more than anyone that trying to develop open code in Octave for MATLAB is a bit of a nightmare. And so it's because MATLAB is designed as a numerical computing language, it's not suitable for use as a general purpose language. I think that transitioning from MATLAB to Python is quite difficult, but very doable. There's a significant amount of people who are doing it, and really the best way to do it is just to have a project and decide, I'm gonna write this in Python instead of MATLAB. If you are a MATLAB user with very limited Python experience, or you have a little bit of Python experience, but you still primarily code in MATLAB, the BrainHack School is a great opportunity to just say, I'm gonna do my BrainHack School project in Python, so be it. And yes, to bring up the point that Pierre made before, packaging in MATLAB is very difficult if you need to compile things. For example, MATLAB has these MEX files, and if you're doing that and working with C code, it can be really tedious. And so packaging is hard across the board. Yes, Pierre's point in the chat, again, just to highlight that he tried to support both Octave and MATLAB compatibility, but it was too much work, dropped MATLAB support at some point, tried to just do Octave, and then eventually just moved to Python wholesale. So why choose Python over other languages? You could argue, and people do convincingly, that Python is the only one that offers the same combination of readability of code, flexibility, the libraries that it supports are fantastic, and its performance is great. You'll hear that Python is described as the quote unquote second best language for everything. And so there's always a language that can eke out in terms of improved readability, improved flexibility, improved libraries, and so on and so forth. But kind of Python ranks really highly across the board for all of those. Again, this doesn't mean you should always use Python. It very much depends on your needs and your community. I'm a big Python proponent. I'm really happy to help people transition to Python because I think that people have a lot to gain from it. But if, for example, your lab, your research group doesn't use Python, it uses a different programming language, and there's resources and support that you have within that group for a different language, that's fine. Keep using that language. But I think that Python in the long term, especially if you're interested in maybe moving outside of academia in the future, is going to be a bit more applicable than most other languages. As I hinted at earlier, you can interface between languages, between particularly R and Python. There are ways to do Python and MATLAB as well. I think actually MATLAB has now added easy ways to interface with Python. There are ways to interface with Python and call MATLAB code, but Python and R are really the ones that have kind of done it really nicely in sync. And so I mentioned that I think that R's statistical software suite is a bit more verbose than what Python has. And so you can work primarily in Python and then fall back on R when you need it, or as someone noted in the chat, vice versa. So really Python kind of gives you the best of all possible worlds in that sense. The core Python data science stack, there are tens of thousands of Python packages that are created by external developers. Sometimes they're huge companies that are creating them. Sometimes it's just one or two people. But I would say that the 6 that I've listed here are perhaps the ones that are kind of most widely used in general data science applications. And honestly, some of these you're just going to absolutely need in order to do the data science work for kind of traditional neuroscience, neuroimaging applications. We're going to talk about the first 3 briefly here, and then other tutorials are going to go into greater detail on most of those others. So I'm going to start off by talking about the Jupyter Notebook because I asked you all to open a Jupyter Notebook. This presentation is designed in a Jupyter Notebook. I think understanding Jupyter Notebooks is important because they're really fantastic resources. So this is a quote: "The Jupyter Notebook is a web application that allows you to create and share documents that contain live code, equations, visualizations, and explanatory text." One of the original purposes was actually to try and kind of usurp traditional publishing means to create kind of a document that had your text that you would write in a manuscript, as well as the code, the outputs, the figures, etc., all in one nice document to improve, ideally, reproducibility. If I give you, the content of my publication, I should also be giving you the code, the data, and everything that I use to generate it. And Jupyter makes a nice self-contained way to do that. You can try it online. Some of you, it sounds like Loic very nicely set up a way for you to do that using what's called My Binder. Tomorrow afternoon, the lecture by Felix Antoine Fortin is going to go into a bit more about Binder and what that is. But suffice it to say, it's a really fantastic resource where you can run Jupyter Notebooks online on a server on the web and work just as you would locally. Jupyter supports many different languages. So traditionally, it was originally built around Python. That's why it has the PY in Jupyter. But it can support other languages. So the presentation that I gave yesterday, I had written it in a Jupyter Notebook, but I was calling the bash shell. You can also write Jupyter notebooks in R. You can write them in Julia. You can write them in a whole slew of languages. And because it's designed openly, it can support pretty much any language. And there's a bunch of kind of people who have developed quote unquote kernels to run other languages. It's best described as a living document around a command prompt. So as you saw, we were able to kind of edit and type as we go and run commands. There's a bunch of various extensions and quote unquote widgets that are built into Jupyter that can make things, you can have interactive figures in Jupyter. It's quite nice. And so it's really extensible in that way. Why would you use Jupyter over, for example, Spider or something? Jupyter is nice because, as I said, it's a self-contained document. I can write up all my code, print all my figures, write some explanatory notes, and then I can give that single file to a collaborator, and they would be able to see everything that I'd done. Versus if you're working in Spider, you may be writing like a traditional Python script, generating figures that you're saving as other files, and then writing up a manuscript elsewhere, and you have to kind of combine all of that and give it to somebody. Jupyter is also nice because you can mix languages even within a given document. We're not going to get into that too much, although I'll talk about it in a second. But I can give you a Jupyter notebook that has some Python code, some R code, some Bash code, all in the same thing, and it's completely interactive. So if I make a change, I can see what happens. The really important caveat, and the thing that's gotten Jupyter a bit of flack, is that the execution order matters. So as you've been running through your Jupyter notebook, you've been creating new cells, executing them as you go. There's nothing to stop you from going through, executing, going back up to one of the first commands you wrote, changing it, rerunning it, and then going all the way down to the bottom. Jupyter tries to make this clear by putting a number next to each cell to tell you when it's been executed, the order it's been executed in, but you can run into some really funky code issues if you start to kind of jump around between your cells. And so it's encouraged that you work linearly through a notebook. And then when you think you may have changed something, you can kind of restart the notebook, run through it and linearly to make sure that it's running as expected. Slideshow mode. As I mentioned, these slides are actually a live Jupyter notebook. We can edit and execute cells on the flies. And the slideshow extension is installed separately. As I mentioned, I'm going to probably later today make a new channel in the BrainHack School Slack for like tool sharing, just cool tools you think people can use. People have been posting in the chat about the different packages for interfacing between Python and R. I think those are great. I think that we should maintain them in a more kind of persistent way in the BrainHack Slack so that people over the rest of the school can benefit from them. But just to give you an idea, this is a Jupyter cell. I could, if I wanted to, change random things as I go, and then go back into the slideshow. Very nice, very fancy, very flashy. Jupyter has built-in LaTeX support for those of you who are mathematicians, statisticians, just like equations to look really nice and fancy. The way that this looks, it renders beautifully. The way that it looks is I use my kind of double dollar sign rather than the single dollar sign that you may be used to in LaTeX, and I can write all of the same kind of LaTeX notation that I normally would. Highly customizable. So you can customize your key bindings if you wanted. You can set different things to try and make your workflow as easy and seamless as possible. And because Jupyter was developed in a very standardized way, it supports a lot of existing standards. You can customize it basically however you want with JavaScript. If you're a JavaScript guru, fantastic, and you want to start using Jupyter and you want to edit it, great. You're golden. For those of us who don't know JavaScript and who still maybe want some customization, there's a whole bunch of extensions that JavaScript developers have written that can make Jupyter work for you in whatever way that you want. One of the things that I really like about Jupyter, and this isn't specific to Jupyter, but it's broader with what's called IPython. IPython stands for Interactive Python. It was created by Fernando Perez, who's over at UC Berkeley. He started IPython as a distraction from his writing his physics dissertation, and then managed to spin it into what is basically now his career, or he's very involved in its development. Jupyter, IPython include a number of these things called magic commands, and they're designed to make your life easier. They are indeed do seem magical. And so they're things like they support inline plotting, timing, debugging, calling of other languages. And so just as an example, one of the things is we can use a magic command to time how long it takes to multiply 2 by 2 exactly once. So the way that magic commands in Jupyter or IPython work is you use a % in a cell, you type the name of the command, in this case the name is time, and then the function you want to run. So my function 2 by 2 gave me 4, and then I get printed that the wall time of this was 21.2 microseconds. So obviously we would assume that multiplication is going to be very, very fast in Python. But sometimes we are running things that kind of can vary from run to run. And we want to see kind of on average, how long does this take? So to do that, we can use the timeit command, magic command. Same deal, % symbol, and then we use timeit 2 by 2. And what this is going to do is it's going to run 2 times 2 about 100 million times, and then report the average amount of time that that command took to run. So it says it took about 7.8 nanoseconds plus or minus 0.037 nanoseconds. And this is the mean and standard deviation of 7 runs, where for every run it did, I believe that is 100 million loops each. So really, it ran this 700 million times to give us this performance estimate. This is really helpful for when you're writing code and you found that your code is taking an incredibly long time to run and you're not totally sure why. You can kind of, if you have a couple different functions and you think it might be one of those functions, you can use this timeit command to kind of see which one is maybe being the time sink. As we mentioned, combining R and Python with the, we can do that in Jupyter. This in the same notebook, even in the same notebook cell, with a magic Python command called the %r command. I'm not going to run that here because I don't have R installed on my local computer, and so it won't work. But for those of you who have Python and R installed, the same way that we used this %timeit up here, you can use %r and then execute an R command as you would there. And there's a lot more documentation for that available online for those of you who are interested in really doing this. One of the things that I use most frequently is getting help in Jupyter. And so there is a help menu available to you in the toolbar. You can press that and it will give you some different Python references, the IPython reference. You can press the H key to see some keyboard shortcuts. As we mentioned, the tab command, when you're typing things, it will pop up with a list of available methods or function calls. Or we can use this prefix a Python function or suffix a Python function to bring up its documentation. So what I'm going to do is I'm going to import NumPy here. NumPy, as I mentioned, one of the third-party packages that's very useful for data science. We're going to get into that in the last part of the lecture. And if I wanted to know what the NumPy function reshape did, I could type numpy.reshape ? And what I get is I get this little pop-out. It looks very similar to the manual pages we saw in the shell tutorial yesterday. Gives me the function signature, so numpy.reshape. It takes the parameters a, new shape, and order, where order has a default. Tells me all about those parameters. This is what it returns, some notes about it, and some examples. So this is the doc string of numpy.reshape. So when we were writing our own function, that documentation string we enclosed in the 3 double quotes. This is why we write those, so that people in the future can kind of read what our functions are doing. It makes it very helpful. We can also prefix any command with exclamation points to run it as an operating system command. And you should use this sparingly. So just as another example here, if I wanted to list the contents of my directory, as we learned yesterday, ls is that. If I type exclamation ls, I'm going to list the contents of the directory I'm in, which is in the on the course repository with all of the materials. I'm under 12-May, 01 Python for data analysis. These are the two files here. Awesome. So next up, we're going to dive into NumPy. Yeah, I think we'll go through this and then we'll take another break after this section. So NumPy is perhaps the most fundamental package for numerical scientific computing in Python. It has the building blocks of pretty much all data analysis you're going to do, and those building blocks are NumPy arrays. So they're n-dimensional, that is, it can be 1-dimensional, 2-dimensional, 3-dimensional, up to, I suppose, if you wanted 100-dimensional arrays. Don't do that. Don't make a 100-dimensional array. Usually like 3 or 4 at most is going to get you what you need. Homogeneous unlabeled arrays. So this unlabeled is going to come into play a little bit later. Working with NumPy is going to look familiar if you spent time in an environment like R or MATLAB. Loic in the chat linked out a nice cheat sheet for MATLAB/Python. There are ones for, there's another one for R as well. But in MATLAB, a normal matrix is a NumPy array here, and in R as well, matrix is the equivalent. The nice thing about NumPy is that it has really optimized routines for creating and manipulating arrays. So what would normally be very tedious, thinking back to our basic data structures in Python, how would I have two-dimensional values? I could have a list of lists of my data, but that becomes very tedious to operate over. And so NumPy has some really nice ways to do that very, very quickly. As I mentioned, the underside of NumPy is written with calling a lot of C, C++, and Fortran functions. And so that means that using NumPy's tools and functionality makes your code a lot faster than if you were doing it yourself using kind of quote unquote pure Python. So we're going to quickly run through some simple examples in NumPy just to get you through the basic operations. The first thing that we'll do is we'll import NumPy as NP. This is a convention that NumPy developers recommend you use. The reason that you would do this is that if you're going to be using NumPy a lot. And so it's really nice to be able to refer to NumPy as just a 2-letter acronym so that I can then in the future type np dot and then whatever methods I'm calling from NumPy rather than having to type out the 5. You think that the 5 versus 2 doesn't seem like a huge distinction. I agree, but it is a convention that the field kind of Python users have adopted. And I strongly encourage everyone who's using Python to work to adopt the Python conventions. That makes it a lot easier for other people to read your code and know what's happening. So importing NumPy as NP is one of those conventions. So we'll run that. And then what we're going to do is we're going to create an empty array of, an empty 10 by 10 array of zeros. So we'll call it array zeros equals, and then the way that we do this is NumPy has a zeros function, and we can provide it a shape. Our shape here is going to be a tuple, and the tuple is going to be the dimensionality of the array we want to produce. So we want an array of zeros that has the shape 10 by 10. And then just to see how that looks, I'm going to print array zeros. And what I find is I get this 10 by 10 array. So 10 rows, 10 columns, printed very nicely. Note the brackets. So those denote distinct columns. So this first column is bracketed, or first row is bracketed, second row bracketed, and so on and so forth. NumPy arrays are really nice in that you can inspect them to learn a little bit about them. So we know that we created this to be 10 by 10, but all arrays have a shape attribute that we can access to see what they look like. So when I print array zeros.shape, I get a tuple and it says, oh, your array is 10 by 10. So I know how many rows it has, I know how many columns it has. We can also print its data type. So all arrays have another attribute called the D type. Here, when I print D type, it says float 64. So we're not going to get into the differences very much between float 64. There's also float 32 and other such things. For all intents and purposes, this is a float, just like we defined back in the beginning of the lecture, almost pi equals 3.14. We can see that that's represented because these all have decimals. Obviously, 0, it's redundant to show 0.00000, so it just truncates it. But if they did have values after the 0, it would display them and can handle them. Critically, NumPy arrays can only have one data type. So I can't have a NumPy array, a basic NumPy array like this, where my first row are all floats and my second row are all ints and my third row are all strings. It doesn't work. And so we'll get into a little bit more about why and how that can be problematic later. Next, what we're going to do is we're going to create a one-dimensional NumPy array with the value 0 through 999. So the way that we would do that is we would say np.numpy has this function a range. And then what we can do is we can say we want to start at 0 and we want to go up through 1000. Again, Python generally is exclusive, so the top number is never reached. So this will generate a vector or a 1D array of the value 0 through 1000. And we can see that like this. So I define this array and now I'm printing it out. Array 1D is an array 0 through 999 is the last number. If we wanted, whoops, that's not quite right. We're going to reshape our array to 100 by 10. So the way that we do that, 2D equals array 1D dot, we can use that reshape function that we looked at before, the help documentation for. So we can call numpy.reshape, and I want to reshape this array, and I want it to be 100 by 10. So the same way before that we provided the size of the array as a tuple, we can do that here. And then we're going to print our 2D array. And so now I have a 2-dimensional array. You'll note that this looks quite different than this 1-dimensional array. There's a lot more brackets. So again, our first row is now 0 through 9, our second row, 10 through 19, and so on and so forth. So we have 100 rows and 10 columns. How are you able to get the matrix to show completely? Mine just shows a line. When you say like a line, I'm not totally sure what is showing, but Jupyter Notebooks, you can, if you click on this little out over here, it will kind of toggle a larger display. So that might be what's happening. Alternatively, if you print the array, that usually gets it to try to show up. So you, okay, sorry. So Emily asked in the chat, how am I able to get the matrix to show completely? Mine just shows a line. Emily created her array 0 through 10,000. So NumPy, by default, when it's printing arrays, if your array is very, very, very big, you don't necessarily want to print it and then it to go on the page and scroll for 10 hours. For any of you who've worked in MATLAB and accidentally like printed out a matrix that's, 10,000 columns by 10,000 rows and then waited for, an hour for it to all print to your screen, you can understand that that's not necessarily useful or helpful. And so NumPy, when it's displaying arrays of a very large size, will truncate them and only show the first few values and the first last few values, or first final a couple final values, just as a kind of help to show you what you have approximately. So we can also multiply every value in our array. So if we do array times 2 equals array 2D times 2, and then array times 2 times 2. What this is going to do is it's going to take every entry in our 2D array, so 0, 1, 2, 3, and multiply it by 2. So note the slight difference in syntax between this and, for example, MATLAB. Here we we just have to use the same multiplication the same multiplication operator as we would to normally multiply like an int by 2 or a float by 2 to multiply element-wise every number in our array by 2. And then we can, if we wanted to, inspect, well, we don't have 50 elements, inspect the first 5 elements. So we can, the same way that we sliced lists to get subsets of the list, we did, random stuff, square bracket, :2 to get the first 2 elements of our list. We can do the same thing for NumPy arrays. And the way that that works is we use the same square brackets and we use the same, for example, colon number. So this will give me the first 5 elements of every row. So if I print that out now, scroll down, or I'm sorry, this is going to give me the first 5 rows. See, I messed myself up. So the first, yes, the first 5 rows, and then if I do a comma, I'm now indexing columns. So I'm saying I want the first 5 rows, and I want the first 2 columns, which is a little bit different than what I'd written here. The first 2 elements of each of the first 5 rows. Let's do that. So I can see, comparing what I've done here, this is the first 5 rows, 0, 20, 40, 60, 80, and it's the first 2 columns, 0, 2, 20, 22, 40, 42, etc. So slicing can be a little bit tricky. It does take a little bit getting used to, but you always index rows and then columns and then every dimension thereafter, and you separate those via commas. I can, instead of doing slices, just grab single values. So let's say I want the 4th value in the first row. I would say I want the 0th row, and I want the 4th value. Again, remember, because Python is 0 indexed, the 4th value is the 3rd index. And so 0, 3 gives me 6, just as I would expect. So everything that you're really going to do in data science and in neuroimaging is going to revolve around NumPy arrays. They are the building block of basically everything that you'd want to do numerical computing on. Pandas adds some really powerful methods for manipulating mixed NumPy arrays. SciPy adds a ton of useful science and engineering routines that operate on NumPy arrays. I think JB is probably going to talk about SciPy Thursday morning for a bit. And SciPy stands for scientific Python. NumPy stands for numerical Python. They're really kind of partners in crime. And then scikit-learn is state-of-the-art machine learning on NumPy arrays. So all of the kind of data science stack relies on your data being NumPy arrays. We're going to take a break here, but before we take a break, I do want to address something that JB just commented on in the chat, which is that slicing, when you slice, you see what we call a view of the original array. And this goes back to the idea, a little bit back to the idea that our variables are pointers, they're not data stores. So when I say array times 2 is 0, I want the 0th row, the 3rd entry, I get 6. This is not copying that number. So I can actually assign a new value to that number. And if I now print out array times 2, come on, scroll down, there we go. I can see now that the 0th row, 4th entry, has been assigned this value. So you can modify NumPy arrays. They are mutable like lists, not like tuples. You can change the values in them. And slicing is a way to quickly access inside a NumPy array, and you can reassign to it. If you want a pure copy of your array, you just want, you want to make a duplicate. So let's say I want to maintain an original copy of this. Original equals array times 2. I can use the numpy.copy method. So what this is going to do is it's going to create a copy of array times 2 and assign it to original. And those are going to be different objects. So now if I see if I can, might be easiest if I hop out of the slideshow for a second. So I just assigned original to be a copy of array times 2. Now if I do original 0, 3, I should get 10,000. Great. Well, I'm going to set it back to 6. And then I'm going to print out original. Fantastic. Original is set back to 6, but we can check array times 2 and see that it's been unchanged. Had I not done copy, had I just done this and just assigned a new pointer, original and array times 2 would both refer to the same array. So now, note I got rid of numpy.copy here. I'm going to reassign in original the 0, 3rd to 6. That's this, but now if I check array times 2, it's the same. So you really do need to be careful if you're making duplicates of arrays and moving them around, that you copy, because as JB commented, that is quite dangerous. David asks, with functions, are variables also passed by reference, i.e. as pointers? Do they become immutable within functions, or can we change them and affect their value outside the function? That's a fantastic question, a bit nuanced, but my answer is going to be officially, it depends. It depends on the variable. If you pass a list or a NumPy array as a variable to a function, so I say, define, change 0, 0, x. Let's say I'm going to accept an array. So x is an array, and my function is going to changes the first entry in the array 0, 0 to 1,000 or 10,000, and then returns an array. So I say x 0, 0 equals 10,000. Return x. So like this, I can define a new function. My array equals numpy dot, let's say, zeros 10, 10, and then changed equals change 0, 0, my array. So what I would expect is changed should be, as we said, the first entry in the first column is now changed to 10,000. What about my array? It's the same. I modified it. So yes, your parameters that you pass to functions, if they are mutable, you can change them even if you don't need to. And so it's important to be aware of that. This can cause some really nasty headaches if you're passing things like lists and you're appending to lists inside the function. You may be modifying the original list. I would say that honestly, this idea of passing objects and changing them is one of the ones that takes a little bit the most effort to get around. Could I copy that function in the chat, please? Yes, just copied that function to the chat. So that's a great question. And JB summarizes that quite nicely. Object references are passed by value. Yes, so that's true. Perhaps not the most clear, but it is accurate. So, object referencing in Python is quite complex, but and you can run into errors. So it's important to remember that if you're changing things like this, you need to be very careful. Is basically what I would say. Go back into this, and then it's 11:06. So I think what we're going to do is we're going to take another. Let's do a 10-minute break. I think we can make it with a 10-minute break. And then what we're going to do is we're going to try working with some real world data with NumPy, and then we're going to get into pandas. So if you can meet me back here, let's say 11:15 is a good time to come back around to this. and then we'll get going with some actual data analysis.
Thanks a lot, Ross. That was excellent. It was, I think you covered so nicely, very important concepts in Python. I think.
Recording. Great. Real world data with NumPy. We're going to try to load some real world data sets that we have made available and perform some basic summary statistics on them. Thankfully, I say both NumPy and Pandas, which we're going to do after this, have functionality for loading the CSV files very, very easily. And nicely, both of them have ways to load CSV files directly from the internet. So rather than asking you to download files to your computer, or for those of you who are using the binder that Loic set up, we're just going to work on reading files directly from the internet. Hopefully this works for everyone. I tested this on a few different computers and a few different Python installations and didn't have any problems. So fingers crossed. What we're going to do is we are going to load some data, and then we're going to take a look at the type, type and shape of the resulting object. So we're going to say data equals, and we're going to use the NumPy function load text. And then what we're going to do is we're going to provide a URL rather than where we would normally provide a path to a CSV. We can provide URLs as well, as long as that URL points at a loadable file. And so here I've made a little bit.ly link to a CSV file. And so I can run this, and that worked for me. And so I should be able to type print data, and I get a data array. It looks like this. As Emily had noted before, this array, this array has a couple ... dots, and that's because it's a pretty big array. So how big is it is a question that we want to know. Print data.shape. It's 506 lines and 14 columns wide. 506 rows and 14 columns. And so rather than showing me all 506 and 14 columns, it just shows me the first 3 rows, last 3 rows, first 3 columns, last 3 columns. So I kind of get an idea of that. If I wanted to see the internals of it, I could again do, show me the 10th row, and it would print that out in full. So I can still use indexing to access those things that I can't see. I did also say that I wanted to take a look at the type of the resulting object. So it's shape and type. So if I print data.shape, data.dtype. So it's 506 rows, 14 columns, and the data are stored as floats. Float 64, again, we're not going to get into the differences of that in this lecture. But it's a float versus, for example, an int. And we can see that here, 6.32. Note the scientific notation is used. NumPy will occasionally, depending on kind of how dramatically different your floats are, will default to NumPy to scientific notation. So right, oh yeah, I was supposed to do that here. Basic NumPy arrays can only have one data type at a time. So even though, let's grab the second one of these columns. So even though, let's say this column, the 4th column is all 0s and 1s in our data set, which we could normally represent as an integer. They don't have decimals. It's useless to do that. They're still represented as floats. And so this is an important concept to know and understand. This is in the 2nd column. This is the 4th column. And so it's going to be treated like a float for all calculation purposes. Now, you might not think that that's an issue, and it generally isn't going to be a huge issue for things like int to floats, where, what's the difference between me saying 0, 1 with the decimal versus 1 without a decimal. There are things known as floating point precision errors. I'm not going to get into those. I think week 3, Greg Carr is one of the TAs, and he's kind of the resident expert on those sorts of things, along with actually most of the people who are going to be at Concordia. You can talk a little bit more about that then if you're interested, but it's just worth knowing that NumPy arrays can only have one data type. So NumPy arrays have some really nice built-in methods to compute summary statistics. So if we want to take the mean of our data, we can just do data.mean. Note that I'm using this dot notation here. So data is our array. NumPy arrays have methods that we can call. So versus functions where we pass our, we pass our variables as parameters. Sometimes our variables have kind of attached functions that are known as methods. And the way that we call that, again, as we did with appending things to our list, random stuff.append, NumPy arrays have a built-in method called .mean. And this is different from the .shape, which is an attribute, because with .shape, we didn't have to provide these brackets or parentheses. Parentheses indicate that something is a function or a method. Versus without the parentheses, it means that it's just an attribute. It doesn't do anything, it just stores a value. So data.mean is going to give us 66.6781698503600703, which is fine, but that is the overall grand mean of the array. Generally, when you're working with kind of data like this, 2D data, rows and columns, one of them, either the rows or the columns, are going to be different data features. Here, we have 506 by 14, just for the sake of kind of readability. Let's assume that this array that we loaded, that we don't really care about what it actually means right now. Let's assume that each row is a distinct observation and each column is a distinct data feature. So if we want to take the mean of each column, we can do that by taking the mean across the first axis. So we want the mean across all of the rows. And we can do that by saying data.mean x, and then providing a keyword argument to this function. So data.mean, compute the mean on data across the 0th axis. And so what I get there is I get 14 values. And these are the means of each of our columns. So to look at some questions in the chat, JB asks, is there a difference between data.mean and numpy.mean of data? So that is there any difference between data.mean or numpy.mean of data? No, there isn't right now. However, they are, for the purposes of this, they aren't different, but they are functionally different, right? I can pass a different array here. So we had that, that array that we defined, array times 2. I can pass that to numpy.mean as a parameter. I cannot call, if I, data.mean is always going to pass data as the parameter to the mean function. So I can't somehow use data.mean and provide array times 2. That's not going to work. It doesn't understand that. So yes, so there is a difference between data.mean and numpy.mean of data, in so much as one, numpy.mean is a function that can accept any parameter. Data.mean parentheses is saying I'm calling the mean method of the data object. So Sivanya asks, does axis always refer to the row? Why do we need to use axis? I can specify different axes here. So remember, data is a 2-dimensional array. So it has 2 axes. It has the row axis and the column axis. So I'm saying I want the mean across rows. If I said axis equals 1, this would say take the mean across columns instead. And so rather than getting 14 values, I'm going to get 506 values. So that is the differentiation between axis there. Yep, Ella, Jake is responding to Ella. Ella asked, is there a way to get the documentation of methods? Absolutely. Data.mean question mark is going to open up this little thing that tells me, returns the average of the array elements along the given axis. And so we can see that it accepts these 4 parameters, and that you should refer to numpy.mean for the full documentation. And so this kind of hints at the idea that this is really just calling numpy.mean, but it's using it with data being that first parameter. Function equals method in Python. Emily asks, is a function equivalent to a method in Python? Yes. However, methods are bound to objects. So I would never just be able to call .mean. A method always belongs to something, versus a function, print, is standalone. This is a function that's not bound to a specific kind of object. And so Loic puts it quite nicely, this whole, a method is always a function is not necessarily a method. So just to get back to where we were, if I print data.mean of, I want the mean taken across rows, across the first axis, and again, because Python is 0 indexed, the first axis is 0. I'm taking the mean across those, so I'm getting the mean of each column. And so we get that here. What about other measures? Can we do other things? Absolutely. NumPy arrays come with a bunch of very helpful methods for calculating summary statistics. So for example, we can print data.standard, standard deviation, which is abbreviated STD, across the rows as well. So here we now have the standard deviation of each of the columns in our data matrix. We could do the minimum. Print data and this is abbreviated min across the rows. And again, that's now the minimum value for each of our columns in our matrix. We can print the maximum, data.max axis equals 0. Now we have the max value for each of the columns in our matrix, and so on. And so there are a lot of very useful commands or methods bound to NumPy arrays that you can call. Again, one of the best ways to see this is to type your array, type dot, and then tab. And now this is going to list all of the available methods that I can use attached to my NumPy array. So we can see things like, you know, max, mean, min, PTP. PTP is going to give me this is a bit confusing. PTP gives you the peak to peak of the array. So that is the maximum value minus the minimum value, also called the range. But they don't use that terminology because that conflicts with some built-in Python functions. Yes, so Eduard asked a very important question, which is what happens if you have NaN in your array? And so we're gonna talk about NaNs in a little bit, but NaN is not a number; it's a missing data value, for example. And when you do this data.max or min or standard deviation or any of these computations, and you have an NaN, the value that you get back is an NaN. So NaN, not a number, plus 1 is not 1. It's NaN. It's not a number. You can't do any math operations with NaN. So I think that's an important concept. As I said, we are going to get to it in a little bit, I believe. I can't remember exactly if I put that in or not. If we don't, I will revisit it at the end because that is a really important concept. I definitely did put it in. It's in the pandas section. So we're going to be getting that in a sec. Subsetting data. So working with our real world data, what if we want to extract certain data observations based on some arbitrary criteria? Let's say we want to examine, outliers in our data. Outliers is a loaded term. I'm sure JB has opinions on this, but for the purposes of us, what we're going to do is we're going to calculate the 2.5 standard deviation range around the mean of our data, and we're going to try and find outliers outside that. So we're going to take the first column of our matrix, first column, And the way that we do that is we are slicing, as we talked about, we can slice NumPy arrays just like lists with the square brackets. Colon here means take all of the rows, comma, take the 0th column. So if I do this first and print out what first column is, it's now just a single column. I can check that with the shape. It's 506. It doesn't, we've just taken that first column. And so now what we want to do is we want to calculate the lower bound of our kind of quote unquote outlier range. So that's the mean minus the standard deviation times 2.5. And then we want the high. So that's our mean plus the first column times 2.5. And so let's look at what those values are. So the lower bound is negative 17.869. The upper bound is 25.096. And then what we can do is we can create a mask for our outliers. So we want to know where in our column values are either greater than our high or lower than our, or less than our low bound. So first column greater than high would give us a mask. So where this is true, it means that entry of first column exceeds our value for high. Just the same, first column less than low evaluates. We can see here that actually all of these are false. There are no values that are less than our low range. But if there were and we wanted to combine them, we would want to make a mask. And so Python has the way that we would do that in NumPy is with an OR command. We want values that are either lower than our low or higher than our high. And so NumPy has these commands, this command logical OR. And what it's doing is it's taking it's computing the OR of each entry in two different arrays. So we have our first column is greater than high. First column is less than low. So these are our two arrays that we saw are trues and falses. And we want to assign this as a mask. So if I print this mask now, this is now an array where entries that are true means that one of these values was true. So either the value in our data is outside the bound is an outlier because it's too high or it's too low. And now what we can do is we can check the values that are outliers. So the way that we would do that is we can just say first column, and then we can use this array, this mask array we created, to subset our data. So the same way that we would normally slice with 0 or 1, we can just provide another array as long as that array is these true false values. This will work. So now we've extracted these handful 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, these 10 outlier values in our first column, which we can see are all quite a bit higher than our upper bound, have been extracted and printed out. So masking data is very useful because generally we do want to operate on subsets of our data that are according to some kind of pre-specified criterion, whether or not it be outliers or you only want subjects for whom you have all available data. You had a couple subjects who dropped out of a study early and therefore they're missing data from the the final couple of sessions. We don't want those, and we can do that by masking our NumPy arrays. Does anyone have any quick questions about this concept of masking or subsetting NumPy arrays with a mask? If not, well, okay, cool. So we're going to go on. What happens now if we want to modify and save data back to our disk? So let's say we are just working off of our normal data. We wanted to multiply every entry by 2 because why not? These were sample scores and we needed to duplicate them for some reason. That's part of the scoring scoring for the questionnaire that our participants filled out. So our modified data, we've multiplied every entry by 2, and now we want to save this. So the way that we do that is the opposite of the way that we loaded the data. So rather than load txt, we want to save txt. And we can just provide the first parameter is the file name that we want to save our data to. And then the second parameter is the data that we want to save to that file. So save txt, we specify the file name, and we specify the data array that we're saving. And so that's not going to print anything out. Nothing is printed to screen when you use numpy.saveText. So now we're going to check that that file is created. I mentioned earlier that in Jupyter Notebooks, you can do this nice thing and make bash calls using the exclamation point functionality. So what we're going to do is we're going to call ls, and then we're going to provide the flags or parameters L and F. L, again, gives us that long format where it tells us like when each file was created. And then F gives us that helpful designation. Is it a file? Is it a directory? Is it a link? Is it a executable? And I just want to know, was modified data.csv created on disk right here? Again, as a reminder, if you provide a file name to ls that does not exist, it gives you an error. So this shouldn't give us an error. And indeed it doesn't. It says, tells me modified data was created on the 12th of May at 11:35. It's 177,000 bytes and it's owned by me. So saving data back to disk, just as easy as loading it in, which is very nice and helpful for people who are kind of modifying their data on the fly. What happens when we have data of mixed types though? So we said that, for example, integers can be represented as floats. Sure, 1 versus 1.0, not a huge stretch. What happens if we have strings? Let's say we have data for participants in a study, and one of the variables that we want to consider is their self-identified gender. So how would we capture that? Or in another study, we were interested in something to do with participants' hair type, what color their hair was. How do we have that? So to do that, I've created there's another link. So we're going to load in some new data from this link, and we're going to do it the same way we did before, just to hammer home. This is how we load in data in NumPy. So if everyone wants to type, data equals numpy.loadText, and then the URL https //bit.ly nds python mixed, and press enter. What you're going to get is you're going to get this really fun error message. And so what it's going to say is it's going to say value error, could not convert string to float. And then it's going to tell you exactly what value in our file it tried to convert to a float. By default, NumPy load text assumes you are loading purely numerical data, and it assumes that you want that data to be stored as floats. If you want your data stored as anything else, you need to specify that. And so unfortunately, our data have strings in it. And so we need to specify that we need our data to be stored as strings. So the way we do that is the same deal, numpy.loadText, the same path. And we're going to provide an additional parameter to our NumPy load text call. And it's called dtype equals string. String here, as I've written it, is how Python tells something that it is a string. So I say dtype equals string. I want all of the data I load in from this file online to be loaded in as a string. So if I do that and I type print data, I now get back my loaded in data. It looks like this. It's a little bit messy, confusing. And I can see that this is mixed data. I have some values that look like they should be strings, other values that look like they should be maybe number integers, some values that look like they should be floats. And then if we inspect the data shape, so if I say print data.shape, this tells me that the data only has one dimension. There are no columns to this data. It just has 41 rows. But we see that it really seems like there should be columns. We have this thing that should be potentially a hair column, something called FSIQ, VIQ, PIQ, weight, height, MRI count. Those things should be separated into distinct columns in our array. The reason that they weren't is because NumPy by default assumes that your delimiter, that is the character that separates your columns, is white space. So either a space or a tab character or something like that. We can see that for some reason, this person chose to delimit their file with semicolons, which is a little bit irregular, but that is no issue. We can still fix it. So we need to specify that in our call to load text. So again, we're going to enter the same command as up above, where we're loading from there. We again need to specify that our D type is a string. And then we also provide this delimiter keyword argument. And we're going to specify that that is a semicolon. So note here, we need to provide the semicolon as a string. I can't just type that. That doesn't work. It needs to be provided like that as a string. And now if I print my data.shape, I get data that has 41 rows and 8 columns, which is close to what we saw up there. And if I just then print the data, I can see that I've separated, these semicolons are gone and things look like they're separated now into each of their distinct columns. So we made it that far. We've got this new data loaded that we want to work with. It has these different data types, some hair color, these different IQ types, weight, height, MRI count. Let's start with trying to get the mean of our data. So if I type data.mean, just as we did up above, that gives me a really strange error. Cannot perform reduce with flexible type. So the only thing here that maybe gave me a hint as to what I should check out is the type word. So I need to check the data type. So if I'm going to print the D type of my NumPy array, they give me this very strange variable, less than U11. NumPy arrays are very strange at holding strings. Again, I reiterated earlier, NumPy arrays can only have one data type per array. So because one of the entries in the array is a string, everything else in the array is going to be treated as a string. And so it's operating on that as a string. We can't take the mean of strings. It doesn't make sense to take the mean of, for example, white versus black hair. That doesn't make any sense. We need numerical data to take the means of. And really, NumPy is best suited for taking the, operating on numerical data in Python. So we need to try something else. So in the last 15 minutes, what we're going to do is we're going to take a crash course into pandas, which it sounds like some of you are familiar with. You were talking about how you use Lambda functions in pandas all the time. Pandas is fantastic. I'm a really big fan. That is what I thought, an uncontroversial opinion, but I have learned more recently that there are people who really don't like pandas for various reasons. To them, I say, bah, I think pandas is great. I think that it has a significant amount of use and utility in basically any field that's using data, doing data science on messy data. High performance, easy to use data structures and data analysis tools, provides data structures very similar to data frames in R, for those of you who use that, or for those of you who are using newer versions of Python, tables. I think tables came about maybe, I don't know, 2015 or 2016. And in pandas, the primary data structure is called a data frame, just like in R. It has some really nice built-in plotting functionality for exploring data quickly. And critically, pandas data frame structures allow you to represent mixed data types seamlessly. So what we're going to try and do is we're going to work on loading back that data, that mixed data that we were trying to get in NumPy with pandas. So as with NumPy, pandas can easily load CSV files either locally on your computer or from the internet, so we can provide the same URL as before. Notably, we do need to specify the delimiter, that semicolon delimiter again, but we're not going to specify the data type. We're not going to say D type equals string. So we need to import pandas first. As before, pandas has a convention. You import pandas as PD. Again, this just makes it really easy. Whenever we want to call pandas methods or functionality in the pandas library, we type pd dot and then whatever the functionality is. This is a pretty widely adopted convention, so I would encourage everyone to use it. So we're going to import pandas as PD, and then we're going to use the pd.read_CSV function to read, again, same bit.ly link, NDS Python mixed. And again, we have to specify the delimiter is a semicolon. So now what I'm going to do is we're going to import pandas, read the CSV, and now I'm going to print the type of object the data is. This is a new function I'm introducing. This is a built-in function to Python. Type tells me what is the data structure of data. And so what I'm going to get is that data is a pandas core frame data frame. And so that's really nice. Data frames are fantastic. We can use this really, really helpful method of pandas data frames to take a sneak peek at the first 5 rows of the data frame. Data.head parentheses, just like how we called data.mean and so on before in NumPy arrays. Head is a method available to pandas data frames, and what it does is it prints the first 5 rows of the data frame. And so we can see those 5 rows here. Jupyter works really, really nicely with pandas data frames, and so I get this like a really beautiful rendering output, unlike what I was seeing with the NumPy arrays before, where I can if I highlight over a row, or move my mouse over a row, I get this pretty highlighting so I can see what I'm looking at. And data frames have some really nice functionality. So we can select columns in data frames using their names. This is similar to how we would select keys from dictionaries. So for example, if I want the hair column of my data, I can do that. And then hair, I can type hair.head, and I'll get the first 5 rows of now my hair thing. I can also select multiple columns. So if I want hair and that FSIQ value, I can do that by providing a list of column names to data. So see here, I just have these 1 square brackets and I provided hair. Here I have the 1 outer square brackets and I'm providing a list, hair and FSIQ.head. And now I see that I got both columns. So this is really, what is the type of hair? That's a great question, JB. Why are those different? So a single column of a data frame is referred to as a pandas series. It has a lot of the same functionality as a data frame, but it's distinct because it doesn't have a representation of columns. It's a single column or a vector. It's like a 1D array in NumPy compared to a 2D array. So we can check that by checking the type of hair, print type of hair using that same function that we saw before. And I see that hair, which was the one-dimensional thing, is a pandas series, but I can compare that now to hair and FSIQ, which is a data frame. So data frames can have multiple columns, have this concept of columns. Series don't have a concept of columns. It's a single entry or single kind of vector. Data frame indexes. So the index of a data frame, it corresponds to the name of each row. So we saw that the top of the data frame that we had a bunch of different column names. So by default, the index of the index of a data frame is generally set to integers, 0 through n, however many rows you have, but it can be set to something else. So up above, we saw that the first column of the data frame was called unnamed 0. We're going to assume that that was meant to be the index. It was meant to be, for example, the participant ID. So we can fix that when we load in the data. The way that we do that is we use data, same thing, pd.read_csv, bit.ly, NDS, Python mixed, again, specifying our delimiter. And now we're going to specify that the index column is the 0th column. So that is the first column that it sees. We actually want to set that as the data frame index. And when we do that, we now see we start at 1 instead of 0 as before. And we have lost that unnamed 0 column. That's now the index, these row labels. This can be made really more explicit and perhaps more interesting because we can set the index directly to other things. The way that we access that is via the data.index attribute. So all data frames have an index attribute, just like NumPy arrays have a shape attribute and a dtype attribute. And we can set that to something, to a list, for example. What we're going to do is we're going to set it to a list. These are actually, let's say, these are participant IDs, but just to be clear, we want all of our participants to be referred to as participant underscore and then their number versus just their number. For whatever reason that we might want. The way that we're going to do that is we're going to say participant, and we're going to use a list comprehension. And I'm introducing quite a few new concepts here that I will get into in a second. Sorry. So the end result is that now our row labels are participant underscore and then whatever the value was. Or whatever our new value is. I've introduced a few things here. One, string formatting. We can format strings on the fly. So we said that strings are enclosed in single quotes. That's great, but sometimes I want to update a string dynamically based on what I'm iterating over in a for loop. The way that I can do that is I can use these little curly brackets inside a string. And the dot format method, all string objects in Python have a dot format method to pass whatever the value is provided to format into the string directly. And then this is the same syntax as our original list comprehensions that we showed. What I'm doing is I'm iterating for every n in range len data. So these are two new built-in Python functions. Len of data returns the length of a data object. Here, len is always the length of the first axis of a data object. So if I have a multi-dimensional array or a pandas data frame, this is the number of rows that I have. And then range just gives me a sequence 0 through, not including whatever this number is. So len of data is going to evaluate here to however many rows I have in my data frame. And then the range of that is going to say 0, 1, 2, 3, 4, 5, and so on. And so I'm creating a new list that's just participant underscore 0, participant underscore 1, participant underscore 2, and so on and so forth as we go through. JB asks a very important question in the chat, which is, should index have unique values per row? Your index does not need to have unique values per row. There are some instances where you can imagine potentially wanting to have duplicate, the same indices for a given row. I personally err on the side of always maintaining duplicate or unique indices for my data frames. And if there's a reason that I'd want duplicates, I generally would like to make that an extra column. This is just about data organization, personal preferences, whatever you would have. Sylvain asks, is there a difference with data.add prefix participant? We can check. So if I do data we're gonna reload the data.add prefix participant data.head. So I would store that. So to answer Sylvain's question, yes, there is a bit of a difference. Data.add prefix participant, that added participants to the column labels. I'm sure that there's probably a way to modify this such that it doesn't do that, but for now, that is what you would do. Okay, so I don't want that to actually be like that. So we're just going to reset it so that we're like this. We're back to this participant underscore 0. The really nice thing about indexes is that we can select rows using their name. So what I want to do now is I want to select participant number 10. The way that I would do that is using this .loc notation. .loc is it's not a method. I don't need to call it with parentheses, but it's not necessarily an attribute either, because I don't, if I don't call it with anything, it just gives me this really kind of opaque thing. I can use it now to do slicing like I would in a NumPy array. So, but critically, I need to use the names. So I could do, give me the 10th participant and I want their hair color. But rather than doing, you know, the entry 10, and then I need to remember what column hair is, it's the 0th column, I can use names, actual names instead. And that's gonna tell me that participant 10's hair is white, which is really helpful. So basically it gives you named access to your data contents, unlike in NumPy. So so the nice thing about Pandas is that calculating summary statistics is very easy. We're running low on time, so I'm going to try and get through this. I think that this content is a bit important. Let's take the mean of our data. So the way that we had calculated the mean on the NumPy arrays with our .mean method, we can do the same. Pandas data frames also have that. And when I do that, it gives me the mean of each of my columns individually. So Pandas, unlike NumPy, I don't need to specify take the mean over the rows. It knows that I probably want to do that because of how the data are stored. It says, I'm going to calculate your mean separately for all of your columns. However, the caveat is it's only going to calculate the means of my numerical columns. So as we said, it doesn't make sense to take the mean of my hair column. So it omits that. So note that axis is equals 0 is not needed. It knows not to take the overall mean. However, I can provide it if I need to, if you really want to, and it will give you exactly the same thing. We can also use this incredibly helpful method to get a lot of stats quickly on a data frame, and that is data.describe. When I do that, for every numerical column, it calculates the count, how many non-missing values there are in that column, the mean of the column, the standard deviation, the min, the quartiles, medians, and max. So this is really nice, quick view of your data. I use describe all the time when I'm loading in data that I'm unfamiliar with, and I think that this is a really nice function. Notice that you may have noticed that weight and height weren't included in those metrics. Those are numerical values. Weight and height should be things that you can take the mean or standard deviation of. And so we need to find out why. To do that, we can check the data type of those. So the way that we do that is we select the columns from the data frame. And then just as with NumPy, Pandas series have D-type attributes. So we can print the D-type of these. And it says that they're objects. We would expect them to be something like floats. And so an object data type in Pandas is really their version of like, I don't really know what it is. It could be a string. It could be something else where we're not totally sure. And so we need to figure out why. So we're going to check our weight column to do that. So I'm going to print weight. And what I can see right off the bat is that participant 1 has this period here in their data. And that might be why my weight column is being interpreted as an object. A period is not a number. If you're familiar at all with like Qualtrics surveys will sometimes export data with missing values as periods. This probably just means that we didn't get a weight for participant 1, which is not hypothetically a problem. We should be able to get around that, but we need to figure out how to do that. And so we can replace values in Pandas data frames with the very helpful data.replace notation. And so what we're replacing is we're replacing all periods with the numpy.nan value. So pure Python doesn't have nan built in. This is kind of like a NumPy specific thing. So we have to say numpy.nan, just like we would math.py, for example. And we want to replace all the entries of data that are periods with numpy.nan, and then reassign that resulting data frame to our data object. So note that I can't if I just do this, data.replace, I get an output where all of my periods have been replaced with nans, but when I then call data in the future, data still has the periods. I need to reassign my output there. And so if I replace all of the dots with nans, I get exactly what I want. So we're gonna now recheck our data.weight dtype and data height dtype. Unfortunately, we see that they're both still objects, which isn't quite what we wanted. We thought that by assigning them to nans, we got rid of those missing values, but unfortunately, Panda said, these were loaded as objects. I'm going to keep them as objects until you tell me otherwise. And so what we can do is we can cast them to a float. Casting is a tool in Python to convert a data object from one data type to another. And the way that we do that is we can say data.weight as type float. And then we now see, the nan is here, and all of the other values have now these added point zeros, suggesting that it's been cast successfully. These are being represented as floats. This is kind of annoying to have to do for every column individually. And so Pandas recognizes that sometimes data are stored differently. And so we can specify this when we load our data. We can tell Pandas what our missing values are. So we're going to go way back to our pandas.readcsv command. We're going to specify the delimiter. We're going to specify that we want our index column to be 0. And we're going to specify our NA values are period. And now when I do data.head, I see that right off the bat, that's the participant 2, their weight is set as nan. And now when I do data.describe, weight and height have been included in this. They are now numerical. And so Pandas reading data in Pandas is incredibly easy. Pandas.readcsv, you can do the pd.readcsv question mark to get the full documentation of all of the possible parameters that you can read, but they've made it really, really easy to read very messy mixed data so that you can do a bunch of operations on it. Unfortunately, we're out of time, so I think we're just going to go right to the summary about Python. Currently sits at the top as the world's most popular dynamic programming language. It's increasingly dominant in the world of data science. I have some family and friends who are, do data science as careers, and it's a mix between SQL and Python as the two things that they kind of live and breathe in the day-to-day. Python, it's relatively easy to learn, performant, that is, it performs quite well, and it has this enormous ecosystem. So thinking of it as the second best language for everything is probably a nice summary of it and way to go. And so I've included some references these references are really from Tal and Neuro Academy, some references for learning Python in the future. Code Academy offers a nice thing, and these are all accessible on the Jupyter Notebook that's on the course materials. So I think we'll take just a couple minutes for questions because I don't want to keep you all from lunch, and then you'll come back around to 1 for containerization with pair. So if anyone has any lingering questions, feel free to ask them now. I'll do my best to answer. Otherwise, you're going to get a lot more opportunities to practice Python throughout the rest of this week and BrainHack School. So you'll get a lot more familiar with all of these concepts that have just been introduced very, very briefly. 3 hours is by no means enough to do an introduction to Python for data analysis. So really you can consider the rest of the BrainHack School as an introduction to Python for data analysis.
But Ross, that was such a great tour of some of the main tools that many of us would be using, many of you would be using. So I think thank you so much for that. It was an excellent tour of things. And I will cover a bit. I will reiterate a couple of things that you covered last in the statistics in Python on Thursday morning. So like if you haven't grabbed everything in the Pandas and things, we'll go over that fairly quickly, but we'll go over that on Thursday morning again.